All right, guys, let's get started. Do some calculus. This is Chapter 1, Limits and Continuity, and Section 1.1, Rates of Change and Limits. So some quick review to get us going. We're not going to do all four of these, but let's maybe take number 1 and number 3. So we're going to find f of 2, just a little bit of practice using function notation. So number 1, if we were going to do f of 2, we'd be looking at 2 times a 2 cubed minus 5 times a 2 squared plus a 4. So that's 2 times 8 minus 5 times 4 plus a 4. That is 16 minus 20 plus 4. That's negative 4 plus 4, and that's 0. That's going to be our answer to number 1. And number 3, f of 2 for sine of pi times 2 over 2. Well, 2 over 2, we can call that 1. Pi times 1 is pi. So this is now just the sine of pi, and sine of pi is 0. So our answer is going to be 0 for that one as well. So if you look in the next 2 slides, you'll see some more questions and the answers to the ones we just did. Hey, we got number 1 and number 3 correct. I encourage you to go back and check out number 4, the piecewise function, number 2, the rational function. If you want some more practice, I suggest 5 through 10. I'm going to leave those for you, though, and the answers follow up on slide 5. So here's what we're going to talk about in this video. We have interpretation and expression of limits using correct notation. I'm going to emphasize correct notation because that's not only important to me, it's important to the AP Calculus test and all of your future professors. Estimation of limits using numerical and graphical information. We're going to talk a lot about how limits can be interpreted in many different ways, one of them numerically, one of them graphically, and then the third one analytically, which means using algebra and properties, and we'll probably spend a lot of time there. Next up, limits of sums, differences, products, quotients, and composite functions. What we're talking about here is the properties of limits, so properties there, and the interpretation and expression of one-sided limits. And finally, the squeeze theorem. If you're in BC Calc, this will be new to you this year because generally it hasn't been in our AB curriculum before. But finally, we begin with limits because limits can be used to describe continuity. They're used to build the definition of derivative, and they're used to build the definition of calculus. And those 3 pieces are the foundation of all of the study of calculus. So we begin then with average velocity. The average velocity of a moving body during an interval of time is found by dividing the change in distance or position. I'm going to go with change in position by the change in time. So a little further, if y equals f of t is a distance or position function, I'm going to talk a lot about a position function this year, a function that gives a position in space at some given time of a moving object at time t, then the average rate of change or average velocity, average rate of change or average velocity, 2 phrases mean the same thing, is this ratio. Delta y over delta x is equal to f of t plus delta, this should say t, minus f of t all over delta t. Notice I'm pronouncing this symbol, it's actually a Greek letter, delta. But in math, sometimes you'll hear this read change in. So the symbol delta, or the letter delta, is used to signify change, where the elapsed time is the interval from t to delta t, or simply delta t, and the distance traveled during this time is f of t plus delta t. So I understand that's very dry, and what I like to do is spice it up a little bit by showing that definition in graphical terms. So got a blank slide in here. I'm going to draw a pretty ugly XY coordinate plane. Let's let t be on the x plane. That's for time. We'll let y be on the y-axis. And let's draw in for ourselves here kind of an arbitrary function. Let's call it y equals f of t. And this is going to be a position function. So here's what we're going to do. I want to analyze my position at some time t. So that will be the point t comma f of t. So this is, we can call it maybe like a starting point. And then at the end of some interval, another point down the road. And this t value or x value, I'm going to call t plus delta t. So what I'm doing here is starting with a t and then adding some delta t time to the original time. So change in time. Why are we using delta for change? Well, we started with this time, we're ending with this time, so it's t plus delta t. So the new y value there is obviously f of t plus delta t. So the change in distance over change in time is calculated like this. We'll take the second distance, which is the second y value, f of t plus delta t, subtract the first y value, that's f of t, all over the second time value, which is t plus delta t, subtract the first one, which is a t, and you can see on the denominator of this ratio here, the t minus t kind of zeroes out, and we are left with f of t plus delta t minus f of t all over delta t. This is average velocity. And it always occurs over an interval. So when we talk about average velocity, we're talking about velocity over an interval. Okay, so in some context, let's talk about a free-falling object. Experiments show that a dense solid object such as a ball or a brick or a book or a rock dropped from rest falls freely near the surface of the earth at y equals 16 square feet or 16 t squared feet in the first t seconds. So how about we turn that into a question? This, by the way, is a position function. And how about a blank slide here? And let's talk about an example. A rock breaks loose from the top of a tall cliff. There's a tall cliff. Here's maybe a little man standing at the bottom. And there was a rock here. And it's going to fall down. Maybe it's going to hit him. But it is falling at that position function from the previous slide, 16p squared. So how about it falls from the top of a cliff? What is the average velocity during the first 2 seconds of the fall? What is the average velocity over first 2 seconds? Okay, so we need a couple of points and we need to calculate the change in distance over the change in time. Well, let's talk about first, time 0, second, time 2 seconds. What is the position at time 0? Well, that'd be 16 times 0 squared, so that's 0. What is the position at 2 seconds? That's 16 times 2 squared, so that's 16 times 4, so that's 64. So the change in distance over the change in time is 64 minus 0 over 2 minus 0. 64 over 2 is 32. And let's label it correctly. That would be in feet per second. So there is your average velocity over the first 2 seconds of the fall of the rock. All right, that brings us into instantaneous velocity. So same second word, different first word than the previous couple of slides. We move from average to instantaneous. The speed of a falling rock is always increasing. If we know the position as a function of time, we do, we can calculate average speed over a given interval of time. But we can also talk about its instantaneous velocity or instantaneous rate of change. The velocity at one particular instance of time. So not the average velocity over a whole 2-second interval, but the average velocity at one particular second, a snap. What was the velocity after 1 second of fall? As we'll see in the next example, we're going to need the idea of a limit to make precise what we mean by instantaneous rate of change. So I have then one more example for you. Let's talk about that same falling rock. So I'm going to draw, let's see, example 2. Let's do another cliff. Let's make it more, maybe there's water under this cliff. And so now we have a swimmer swimming in the water. Here's this big, big rock, and it is about to fall. So the question I have for you this time is find the velocity at the instant. Find the velocity at the instant. Time t equals 2 seconds. Okay, so a bit of a different thing there. Now, we have already calculated the delta y over delta t in this situation, but now I want to think about it a little bit more, I guess, theoretically, because we're not talking about some situation where we have a point and then another point and the average velocity over the whole time. We're talking about one particular moment in time. So maybe we can think about this as if this second point were actually so close to the first that they were on top of each other. So close that maybe the distance between the two of them, I'm going to use the letter h here, is practically nothing. So how about we try that? So maybe we look at a situation where we have one point in time, t equals 2, the second point in time, t equals 2 plus h, and kind of see what happens as we look at h going to 0. So here we go. Let's calculate the delta y over delta t. So our second position in time is that f of our 2 plus h. So in our case, that's going to be 16 times 2 plus h quantity squared, minus the first one. So that's plugging in the value of 2 to the function. So that's 16 times 2 squared. This is all over our second time, 2 plus h, minus our first time, 2. So let's simplify that a little bit. 16 times, let's see, 2 plus h, expand it out, that's 4 plus 4h plus h squared, minus 16 times a 4, so that's 64. This is all over 2 plus h minus 2, that's just an h. Now expand it out. 16 times 4, 64. 16 times 4h, 64h. 16 times h squared plus 16h squared minus a 64 all over h. The 64's zero out. We're left with 64h plus 16h squared. There's an h on the bottom still. If we factor out that h from the top, 64 plus 16h all over h, where the h's cancel, and we end up with 16h, or actually, let's call that still 64 plus 16h. Now, not an answer. What did we say about this h? Well, we really wanted this h to be practically nothing. We wanted to calculate instantaneous velocity, so not the velocity over 2 spaces, but exactly at 1 space. So that means h is nothing. I'm going to write it here, practically 0. So that means we're left with 64. And this is a velocity, so it's in feet per second. And there we have it, 64 feet per second. This leads into the idea of what's called a limit. When you have a quantity in a calculation, in this case it was h, that you would like to send as close to a given value as possible without actually being that value. So that will take us to the next video, and I'll meet you back there.